Welcome back. This is CS 480, 680 Introduction to Machine Learning, as taught at the University of Waterloo in fall 2024. And this is lecture 6, which is support vector machines. It's going to be the first part of a multi-part lecture. And today we're going to talk about maximum margin classification. It's going to and constrained optimization. Okay, so yeah, today we're talking about the maximum margin classifier. So what does that mean? And so it relates back to the perceptron algorithm that we talked about a few weeks ago, which is a foundational method for learning linear classifiers. And so the perceptron algorithm works by iteratively adjusting the decision boundary until it finds a feasible solution that correctly classifies all the training data, of course, assuming that the data is linearly separable. However, while the perceptron guarantees finding a separating hyperplane, it doesn't prioritize at all which one it finds. And so as a result, the hyperplane it learns might not be very robust. And so even though the perceptron succeeds in classifying the training data correctly, slight perturbations or noise in future data could cause misclassifications. And so this lack of robustness can lead to poor generalization performance. And so, to give you an idea of what I mean, on this figure on the left here, the perceptron algorithm could find any one of these separating hyperplanes. We can see that some of these might be better than others, or this hyperplane here. There's points that are really close, really close to that boundary. And so if there's a slight perturbation in the training data set, then we would start to get misclassification on the testing data, or when we put the model out in the world to deploy it. On the other hand, this one straight down the middle here, there's a bit more of a gap between the training data points and where the decision boundary is. So that the perturbations in the training data sets would have to be larger in order for the performance on the training data set to be compromised significantly when we move to the testing situation. And so this is the idea of margin. And so the margin is the separation between the closest training point and the decision boundary. And so we say that a large margin ensures the classifier is more resilient to noise and variations in the data, improving its ability to generalize to new unseen examples. And so on the right, so we've got a specific separating hyperplane with showing the classifier's decision regions. And so a large margin classifier ideally would ensure that new observations falling within the blue region will reliably be classified as blue, and similarly for the purple region. And so today, we're going to think about if there's a way to maximize the margin. So a method to find not just a feasible solution, but an optimal separating hyperplane that would give us the most room for error on either side of the decision boundary. And so what we're going to be going into today apparently warranted a warning from the authors of the Elements for Statistical Learning. So they decided on this particular section to include, the heads up. You might want to skip this part because it's technically difficult, maybe not necessary for you to understand the rest of the text. But it's also not necessarily in a fun way. This is Edvard Munch's The Scream. So they're telling us that if you embark on trying to understand this, you might just have an existential crisis. And so honestly, I found this material challenging. So we're going to be dealing with some hard math today. So yeah, just a heads up that is gonna be challenging material. Um, and yeah, we're thinking about perceptrons again, so I'm bringing back the matrix memes. Um, but yeah, if this material is so hard, why are we taking the trouble to go and understand this? And so understanding, you know, yeah, so why are we going down this rabbit hole, for lack of a better word? And yeah, so understanding what we're going to talk about today is really key because it laid the foundations for one of the most important advancements in AI, which is support vector machines, or SVMs. And so SVMs are among the most powerful tools that we have for classification. And their strengths comes not from this idea of finding the hyperplane that not only separates the two classes, but does so in the most optimal way. And that is by maximizing the margin between them, as we'll see. So we're going to take a first glimpse at them today, and then over the next couple of lectures, discover some generalizations that make them really powerful. So yeah, it wasn't just about finding a better classifier. It's a key innovation that really helped push the field of machine learning towards robust, reliable, flexible models, and it's had a lasting impact on the field. So yeah, the math is going to get tricky, but trust me, um, if you're willing to engage with this, we're going to come out with a really deep understanding of one of these cornerstones of ML. Okay, so we're interested in maximizing the margin, and where we'll be taking the margin as the distance between points and the decision boundary. But yeah, before we go any further, let's do a quick recap on separating hyperplanes. So let's say we've got a point xi shown in dark red here, and we want to know how far away it is from the decision boundary denoted by the dashed black line. So let's consider yeah. So the way we do that is we can think about some arbitrary point x that lies on the decision boundary, and then we can call the vector that connects xh to xi v. And so now we can see that v can be decomposed into orthogonal components, and that we're interested in the shortest path from the point xi to the decision boundary that's perpendicular to the boundary. So that's this point in orange. And so to recover this component, we can find the projection of V onto the surface normal of the hyperplane, where the surface normal is the unit vector whose direction is shown by the dotted black arrow. And so that this is equal to the weight vector divided by the normal difference. And so yeah, if we do this, we recover the signed distance from a point to the decision boundary is given by the inner product of the weights plus the bias, all divided by the norm of the weight vector. Okay, so now that we know how to compute the distance between a point on the point and the decision boundary, let's see if we can define the margin. So we thought about this a little bit when we studied the perceptron algorithm, but let's see if we can get a bit more specific. So the margin refers to the distance between the decision boundary, or the separating hyperplane, and the nearest data point from either of the two classes. So equation at the top here describes how the margin, which we'll call gamma, is computed. So the margin is defined as the minimum distance from the hyperplane to the closest point among all points. And so this distance is expressed in terms of the vector that parameterizes the hyperplane W and the labels and the data points. And so we incorporate the labels yi to convert the signed distance from the hyperplane into an unsigned distance, and so to ensure that the margin always stays a positive value. And so Crucially, we can see that the margin is inversely proportional to the inverse of the norm of the weight of the hyperplane's weight vector. And so the norm essentially measures the magnitude of this weight vector. And so a larger norm corresponds to a smaller margin. And so this is interesting because it suggests that in order to maximize the margin, we're interested in minimizing the norm of the weight vector. Right, so the scatter plot here shows the margin. So we've got two classes shown in blue and red, which are separated by a decision boundary represented by the dashed line. The margin, specifically twice the margin, associated with the solution is depicted by the distance between these two parallel lines here. Between these two parallel hyperplanes that run alongside the decision boundary. So these lines, this positive margin here passes through the closest point of the positive class, the red class, and so this is the closest point from any of the class, and so this one defines the margin. Right, so yeah, to sum up, the width of this margin represents how far the decision boundary is from the nearest data points of either class. So, right, so today we're turning our attention to the maximum margin classifier problem. This is concerned with finding the optimal decision boundary that maximizes the margin between two classes. Right, and so as we said, our goal here is to find the parameters that define the hyperplane, the weights and bias, that minimize or that maximize the margin, but then the margin is defined as the minimum distance to a data point from either class, as I've got here. So we want to maximize the margin, but then the margin itself is a minimization problem over distances, but distances from the hyperplane to the training data points. So it's not just a simple optimization task, because it's actually what we call a bi-level optimization problem. And so, yeah, in this situation, we've got one optimization problem nested within another. And so the outer optimization problem, or the upper level task, is to maximize the margin. And then on the inside, we've got this lower level task of finding the training point for which we can recover. We have the smallest sign distance between the hyperplane, or the smallest distance between the hyperplane and the closest data point. And so, yeah, directly trying to optimize this kind of problem is pretty complex, because it would require simultaneously solving two nested tasks. And yeah, so basically to give us a visual explanation of what we're trying to do here, is that we would pick a margin, and this is associated with one closest data point, but then we would pick another margin and maybe find another point. Another margin would give us another closest point, and so this would be hard to do. Okay, so yeah, is there anything we can do to make this problem easier? And so an important property of the half space hypothesis class is that scaling the parameters, both the weights and the bias together, this doesn't change the decision boundary itself. So no matter how we scale the parameters, the position of the decision boundary stays the same. So in the left plot here, we've got a boundary defined by a particular set of weights and a bias, represented by this dashed line. And so the points where the boundary intersects the axes are determined by the ratios of the bias to each weight. So it's these ratios are what define the position of the boundary in the space. Okay, so now if we scale both the weights and the bias by the same constant, let's say 5, then the decision boundary remains unchanged. We've applied a scaling factor of 5 times for this middle plot, and then 100 for the right plot. It doesn't matter. The intersection points along the axes stay fixed. It's always minus b over over the feature weights. So this reveals that the decision boundary has a scale invariant property. So if we scale all parameters together by any constant, we don't affect the boundary. Right, so the decision boundary just depends on the ratio between the weights and the bias, not their absolute values. So if you were to change the weights alone, the angle of the decision boundary would change, so it would kind of rotate around, altering its orientation. And if you change the bias alone, you would translate the decision boundary along the line of its normal direction. But when the weights and bias are scaled together, the ratio remains the same. So we keep the decision boundary fixed. Okay, so a scale invariant decision boundary also has implications when it comes time to compute the signed distance between any point in the feature space and that boundary. Specifically, because jointly scaling the parameters doesn't change the decision boundary, the distance from any point to the boundary remains unchanged as well, regardless of how much we scale the parameters. In previous models, like the perceptron, we were primarily concerned with the sign of the linear predictor, the inner product between the parameter vector and the feature vector plus the bias. So in other words, we just cared about whether a point was on one side of the decision boundary or the other. But now we're not just interested in which side a point is on, but also how far it is from the boundary. Right, so in these equations on the left here, this is the distance calculation that we saw earlier, but now we've applied a scaling factor to W and to B at the same time. And so if we apply it to W, then we also need to incorporate it inside the norm of the weights. In which case we can factor this out, and then we'll just get A over A. That's going to leave us with exactly the same distance that we had before. And so, yeah, we scale everything by a constant. The boundary doesn't move, and the distance from any point to the boundary stays exactly the same. So this is illustrated in the plots on the right. So in the leftmost plot, you can see a set of weights and bias that define the decision boundary, with the linear predictor and the Euclidean distance to a particular point. And so when we scale the parameters by a factor of 5, we can see that the linear predictor grows, but then the Euclidean distance is still exactly the same. And so we scale by 100. We've still got the linear predictor grows again, but we've still got that exact same Euclidean distance. Okay, so how does this help us? Well, we could change our goal to just demand that the linear predictor or decision function, Wx plus b, be equal to +1 or -1 for the closest data points. So the closest point would be 1 unit of margin away from the decision boundary. So we're allowed to do this because if during optimization the linear predictor was outputting larger or smaller values than 1 for the closest point, we just rescale the weights and bias to make the margin exactly 1 unit wide between the boundary and the decision points. So making this choice gives us what's known as the canonical representation of the decision hyperplane, which is depicted here. And so here we have 3 lines. The central dashed line represents the decision boundary, which is where the classifier predicts an equal likelihood between the two classes. And mathematically, this is the set of points where the decision function equals 0. And so the hyperplane that divides the two regions or half spaces, and points on one side of the boundary belong to one class, and points on the other side belong to the other class. And then on either side of this decision boundary, we have 2 parallel lines, one in red, one is blue. And so these are the margins associated with the classifier, or a particular separating half space solution. So yeah, the red corresponds to the set of points where the decision function equals +1, and the blue line corresponds to the set of points where the decision function equals -1. So if we bring this idea back into our objective, we have a new way of thinking about the problem. We no longer need to directly maximize the margin. Instead, we can optimize over the weights while ensuring that all points are correctly classified with an imposed margin. So we can reframe the original nested original optimization problem as a constrained optimization problem. Right? And so yeah, we had an original nested optimization problem, and now we can have a constrained optimization problem. And so as maximizing the inverse of the norm of the weights is equivalent to minimizing the norm of the weights, we can rewrite the objective as a minimization, where before we had a maximization, now we've got a minimization. And also we can choose for convenience to minimize half the squared norm. And so we can do this because the squaring function is monotonically increasing for non-negative values, and the norm is always greater than or equal to 0. And then because the half factor is just a scalar, this also doesn't change the location of any extremum. And so we do these things for later convenience. And so this transformation matters because solving a constrained optimization problem is more straightforward than a nested optimization problem. Additionally, our algebraic manipulations have turned this into a quadratic optimization problem, where we minimize the size of the weights, the square of the weights, subject to linear constraints that ensure the data are correctly classified. And so this is especially convenient because a quadratic optimization problem with linear constraints has a unique minimum. So there's a single optimal solution where the weights and bias that maximize the margin and provide the most robust decision boundary possible. Okay, so to drive home what it is that we're trying to do when we talk about constrained optimization with inequality constraints, we can focus on a simplified case where we assume that there's no bias, so we're dealing with a homogeneous function where the decision boundary passes through the origin. So yeah, the left side here, I've got a scatter plot depicting the data set we wish to classify. Our goal is to separate these two classes, shown in red and blue, using a decision boundary that might be something like this. And so it's this boundary that we want to optimize specifically to maximize the margin between the two classes. And so on the right side, we have a contour plot that represents the corresponding optimization problem over the parameter space. So yeah, we've been dealing with things in fairly mathematical way, just try to provide a visualization of what's going on. So these concentric curves show level sets of the quadratic objective function. And so this is which is half the squared norm of the weight vector. So as we move away from the origin, this half norm of the weight squared increases, which is not what we want. So yeah, we want to minimize this quantity, which geometrically would mean we're trying to push the weight vector towards the origin to reduce its magnitude. And so the center of the contours, this darkest region, represents smaller values of the objective function. And as we move outward, this increases. But we can't just pick anything. This minimization is subject to a set of constraints. Specifically, we need the classifier to actually correctly classify all the points. And so there are many possible parameter choices that could do this. But the ones that actually work define the feasible region in the parameter space. And so we've depicted this here in this white shaded area. So this represents the set of weight vectors that correctly classify the points according to the margin constraints. And so our optimization task is therefore to find the points within this feasible region that minimizes the objective function. And so this would correspond to the weight vector with the smallest norm that still satisfies the constraints. And so the feasible region ensures that the classifier correctly separates the classes, while contours of the quadratic objective reflect the goal of minimizing the norm of the weight vector, ultimately maximizing the margin between the classes in feature space. Again, this represents a simplified case where we don't have a bias, but that made it easier to visualize. Okay, so how can we solve a constrained optimization problem? So let's look at a simple problem, minimizing the quadratic function with the constraint that restricts the variable to be greater than or equal to 5. So this quadratic function that we're trying to minimize is shown in this graph on the right, where we can see a typical, characteristic U-shaped curve of a quadratic function. And so this shaded region on the graph highlights the feasible region where the constraint applies. And so while the function has a natural minimum in the unshaded region, like outside, we're only interested in solutions to the right of x equals 5. Okay, so how do we solve this kind of problem with constraints? And so one approach is to use something called Lagrange multipliers. And so Lagrange multipliers provide a method for incorporating constraints directly into the objective function. And so instead of handling the constraint separately, we combine it with the original function into a new expression, which we call the Lagrangian. And so that's what, yeah. And so this is what we use to solve for both the original variable and the Lagrange variable. And so the new Lagrangian function contains both the original objective and a term that accounts for the constraint, weighed by a new variable lambda, which called the Lagrange multiplier. And this is restricted to be non-negative. And so the Lagrange multiplier tells us how much the objective function would change if the constraint were to be relaxed or tightened. And so if lambda is positive, is greater than 0, the constraint is said to be active and plays a role in determining the optimal solution. And so once we set up the Lagrangian, we solve it by taking the partial derivatives with respect to both the original variable x and the Lagrange multiplier lambda, and then setting them equal to 0. And so this process gives us a set of conditions to find the optimal solution. In this particular example, we see that the Lagrange multiplier is lambda equal to 1, which tells us that the constraint x greater than 5 is active. And so this brings us to an important concept, the idea of an active constraint. Here, the optimal solution lies exactly at the boundary of the feasible region. Yes. And so, yeah, a constraint is said to be active when it directly affects the outcome of the optimization. The Lagrange multiplier being positive indicates that the constraint was crucial in determining the solution. Okay. So let's now consider a slightly different situation involving the same quadratic function, but a different feasible region. And so unlike the previous example where the solution landed exactly on the boundary of the feasible region, here the minimum of a function occurs actually within the interior of the feasible region. So the constraint is not binding in this case. And so we still use the Lagrangian method to incorporate the constraint into the objective function, just like before. We take the partial derivative with respect to the variables to optimize the objective function, and the partial derivative with respect to the Lagrange multiplier to enforce the constraint. So we set both partial derivatives equal to 0 to find the optimal solution. So in this case, when we solve the Lagrangian, we find that the Lagrange multiplier is 0. And so this tells us that the constraint is inactive, so it didn't actually influence the solution. And solution, as the solution lies well within the feasible region, the constraint has no impact. And so this is an important concept because it shows that not all constraints will actively shape the solution. So when constraint is inactive, the multiplier is 0, indicating constraint does not affect the result. Yeah, you might wonder that, if since the constraint is inactive, couldn't we have just solved this problem by minimizing the original objective function directly without needing to consider constraints? But yeah, when solving constrained optimization problems, we don't always know in advance whether the constraint will be active or inactive. And so that's why we still need the Lagrangian approach to help us determine whether the constraint actually matters in the optimization process. And this is especially true when we have lots of constraints to deal with. As the Lagrangian method, Lagrange generalizes well if we have more than one constraint. And then for each constraint, we introduce a new Lagrange multiplier, a new lambda to account for that constraint. And so each constraint can either be active, in which case the multiplier is positive, or inactive, where the multiplier is 0. So the constraint doesn't play a role in determining the solution. Okay, let's see how we could apply the Lagrangian approach to the maximum margin classification problem. Okay, to recap on our progress so far, we were originally maximizing the margin directly in this kind of nested optimization process. And then we reformulated this as minimizing the half-squared norm of the weight factor, subject to the constraint that every single point in the data set is classified correctly, and that the linear predictor returns a minimum value of 1. In other words, for each point, the classifier's decision function times the actual label must be greater than or equal to 1. And so since there's a constraint for each point, the Lagrangian will involve introducing a Lagrange multiplier for every point in the data set. And so each of these is subtracted from the objective that we seek to optimize. So we express this as a sum. And as before, the multipliers must be non-negative, since they only activate when the constraints are violated or exactly met. And so to relate this back to feasible regions, we can think about the geometry of what's going on. If we consider the decision boundary represented by the dashed black line and the two parallel lines associated with the margin, the points closest to the boundary, where the constraints are most likely to be active, we might expect here the Lagrange multipliers to be non-zero. Points further from the boundary, maybe those back here, we would probably expect that those multipliers might be 0 because the constraints might be naturally satisfied without their influence. So there are some insights we can glean even before we've solved the problem, particularly regarding the Kruskun-Tucker conditions. And so these provide the criteria for optimality in the maximum margin classification problem. Basically, they ensure these conditions ensure that we found the best possible solution to our constrained optimization problem. So there's four of these such KKT conditions. The fourth condition that I haven't listed here is stationarity, which ensures that the gradient of the Lagrangian with respect to the primal variables is 0. So it's important for finding the optimal solution. Primal feasibility ensures that the constraints of the original problem are satisfied, so that each data point is either correctly classified or lies on the margin. And then dual feasibility, and in our case, this ensures that the Lagrange multipliers are non-negative. So this makes sense because the Lagrange multipliers only activate when the constraint is tight or violated. Complementary slackness. So this condition connects the primal and the dual solutions. And so complementary slackness says that for each constraint, either the corresponding Lagrange multiplier is zero or the constraint is active. And so this has important implications for how our model works, because for each data point, one of two things is going to happen. If the Lagrange multiplier for a point is zero, this means that it's correct. It's probably correctly classified in such a way that the constraint isn't tight. So we might not expect these to contribute to determining the position of the margin or decision boundary. On the other hand, if the Lagrange multiplier for a point is greater than zero, then it's directly influencing the outcome. That point would there would be an active constraint for that point. Okay, so can expand the Lagrangian into four terms by multiplying lambda I and yi through this term inside the brackets involving decision function, and then finally to the last one at the end. So that gives us this expression in the second line here. And then to find the optimum, we need to satisfy that stationarity condition. So we take the partial derivative of the Lagrangian with respect to both the weights and the bias. So yeah, let's first look at the derivative with respect to the weights. Yeah, in this case, partial derivative with respect to W would only need to consider these first two ones. So the 2 would come down, cancel out this half, and then we're left with a single W, so that goes there. And then the derivative with respect to W of this term gives us this sum over lambda I, yi, and xi. And then if we set this to 0, what we arrive at is a new constraint that tells us that the parameter vector is expressed as a linear combination of the training data points. And so it's a really important result because it means that the weights aren't defined directly by the individual features, but instead by a combination of the data points themselves. So they're each weighted by the corresponding Lagrange multiplier and class label. Okay, so moving on to the partial derivative with respect to bias, taking this derivative and setting it to 0 gives us another important condition, which is that the sum of the product of the Lagrange multipliers and class labels must equal 0. And so this ensures that the decision boundary is kind of correctly balanced between the two classes, and that it's kind of like there's a balance between the two classes here. And so the key takeaway here is that we've now expressed the model parameters W in terms of training data points, but then because of the complementary slackness condition, we know that many of these lambdas will be 0. So points that are far away from the decision boundary, that aren't actively enforcing the constraint, they're not going to play a role in determining this weight factor. And so the points for which lambda are positive, for which they're greater than 0, we have a special name for them as support factors. These are the ones that are closest to the decision boundary, and they play a crucial role in determining the margin. And so there's a very practical takeaway in that, after the model is trained, many of these data points actually become irrelevant. So once the decision boundary is set, only the support vectors, the points for which the Lagrange multipliers are greater than 0, those are the only ones we need to keep around. So these are the ones that lie on the margin. and these are the only ones that directly affect the classifier. All the other data points with the Lagrange multiplier 0, these can be discarded because they don't contribute to future predictions. And so we call models of this form support vector machines because they're computationally efficient, especially when working with large data sets. As only a small fraction of the points we need to keep around to define the decision boundary. But yeah, in order to solve the problem, we need to find those Lagrange multipliers. So we need an expression uniquely in terms of the multipliers and our training data. Okay, so what do we know? We've got the Lagrangian copied over at the top. So this includes the term for minimizing the squared norm of the weights and the terms incorporating the constraints via the Lagrange multipliers. We also now have an expression for the weights derived by taking the partial derivative in the last slide. And this is the linear combination of the data points weighed by the Lagrange multipliers and their corresponding class labels. We also derived a condition that the sum of the Lagrange multipliers times the class labels must be 0. And so yeah, once we and then we also still have the non-negativity constraint on the Lagrangian multipliers. Okay, so we can substitute the expression for the weights into both the first and the second terms. So yeah, representing the squared norm of the weights. And these are going to expand further into these double summations. So these account for all pairwise interaction between the Lagrange multipliers and their associated data points. Yeah, and then after expanding these terms, we still have some remaining terms that involve bias. But we've already identified that the sum of Lagrangian multipliers times the class labels must equal 0. So we can just eliminate this term involving the bias. As we can simplify even further by summing the two terms as they're scaled versions of one another. So putting these two together. And then we arrive at an expression that's fully in terms of the Lagrange multipliers and the data points. So the objective is now to maximize the dual Lagrangian with respect to these Lagrangian multipliers, subject to the constraints that the Lagrange multipliers must be non-negative. So yeah, exactly how one solves for the lambdas is beyond the scope of this lecture. And in this course, we'll just use an off-the-shelf package to handle that. So I played around with a few Python packages for convex optimization and had luck with this one called CVXPy. So this is an example from their documentation page. This code here is an example from the documentation page. I found the interface really intuitive. So you're going to start off by defining what your variables are. So in our case, this would be the lambdas. You feed in, and then you feed in the objective, which would be this is the objective in our case, and then the constraints. And so for us, this would be that lambda i's are not negative, and that the sum of the product of Lagrange multipliers and training data labels is equal to 0. And so once this problem is defined, I just solve it. Combine everything into this problem, and then you just go problem.solve. This would give you the optimal values for your variables. In this case, we would want to use the maximum method. Right, and then after that's all done, you can go ahead and analyze and access the variables as normal. Right, and so once you have your lambdas, you could finally actually compute the weight using that constraint we derived earlier, and solve for the bias term B for your support vector machine. And so how do we solve for B? And so here we can exploit the knowledge that for any point that is a support vector, the decision function evaluate that point is 1 for points in one class and -1 for points in the negative class. And so this condition holds because support vectors lie exactly on the margin. And it's where the classifier's confidence is highest. And so we can rearrange this equation to solve for the bias term B. And so by isolating B on one side, we can express it in terms of the weights and the support factor. And then the bias is simply the negative of the inner products between the weight factor and the support factor scaled by plus the class label of the support factor. You can get a more robust estimate of B by averaging over all support factors. So where NSV is the number of support factors, and the sum indexes over the set of support factors. And so since the decision boundary is determined by all support factors, we take the average of the bias values to compute computed for each support factor. So yeah, in practice, we take the average to ensure that the decision boundary reflects the contributions of all of these critical points. Yeah, so does it work? Yeah. Coded this up in CVXPy, and we can see that it found a decision boundary that cuts right between the two classes, and it found the support factors, which are those points right on the margin. And yeah, I only used these training data points to construct this decision boundary and recover the bias. After all of that weird math, it actually did something that looked useful. Okay, so to sum up what we talked about today, so we talked about the need for maximum margin classifier as it relates to ensuring robustness, reducing sensitivity to error, and also giving that generalization that we want. We also talked about and defined the margin and how it's absolutely this definition is absolutely fundamental to this classification, this optimal separating hyperplane problem that we've taken on today. We also saw how Lagrangian multipliers can be incorporated to derive this dual of an optimization problem where we've got with inequality constraints. We also saw how to interpret the solution to the dual objective. So once we actually solve the problem and get our lambdas, what does that mean? And so we used language like support factors, active and inactive constraints, the KKT conditions. We also saw how to just apply an off-the-shelf solution to solve the quadratic programming problem, and then actually use that solution to go ahead and predict class labels, as well as identify support factors. And then, yeah, last but not least, talked about this fundamental practical advantage of SVMs in that they provide a very sparse solution, in that the final parameter vector that we compute is a weighted combination of just a few training data points, specifically those that lie on the margin. So we don't need to keep all of our training data around. We can just compute, keep a few points around the ones on the margin, the ones for which the constraints are active, and that's all we need to train our model. All right, thanks for your attention. We'll see you back here next time, where we'll be continuing on to talk about support vector machines.